Hey, welcome back everybody. We're going to talk about the kinetic collision model as it relates to equilibrium systems. So the first box at the top of our page here says, in the kinetic model, a successful chemical reaction requires that the appropriate reagents collide with sufficient energy. Meaning they have to smash into each other with sufficient energy to break existing bonds and make new bonds. So they have to overcome a certain energy threshold. If they bump into each other too lightly, no reaction. So if the collision has sufficient energy, it'll move forward. If it doesn't, it won't. The second criteria is they have to collide with a specific orientation. It's kind of like when you're trying to put two pieces of Lego together. If they're not facing in the right direction, they won't connect. No matter how hard you push the bumps into the other bumps, they're not going to come together. So because every molecule has a unique amount of energy requirements, and each of the molecules in a chemical reaction have a specific orientation, a unique shape, this varies from each reaction to each other reaction. So the amount of energy and the orientation is specific to each chemical reaction, which is why every reaction occurs at slightly different rates. So let's take a look for a moment at time zero. We're imagining that A's and B's are bumping into each other, forming C's and D's. So at time zero, we've got a bunch of A's. And we've got a bunch of B's. Now, the collision frequency between A and B is high. There's just so many A's and B's. So when this A and this B collide with one another, or when this A and this B collide with one another, a reaction occurs. So the collision frequency between A and E is at a high rate. If there aren't any C's and D's to collide initially, then the collision frequency between C and D is 0. They're not smashing into each other at all. So if we have to describe the relative rates of the forwards and the reverse reaction, if A plus B forming C plus D is the forward reaction, it occurs at a high rate. And the reverse rate, the C and D forming A and B, that reaction, the reverse rate is not happening at all at time zero. All right. So now at time number 1, we've still got some A's and B's. But now we see the formation of some C's and some D's. So the collision frequency between A and B is somewhat reduced here, because not just are A's and B's colliding, but A's and C's are colliding. An A-B collision would result in a reaction, but A and C collision, there would be no reaction. So the collision frequency between A and B is reduced, meaning the rate is slowing down. Still pretty high though. What would the collision frequency between C and D? Well, back at time 0, it was 0 because there weren't any. But now that we have some C's and D's, every now and again, a C and D will collide and a reverse reaction will occur. So the collision frequency between C and D is still pretty slow, but it's increasing. So here's our relative rates. Our A plus B rate is fast, but slowing. Our C plus D forming A plus B is slow, but it's increasing. Meaning that as C's and D's begin to build up in our reaction system, the collision frequency will increase and the rate will increase. As A's and B's are consumed by proceeding in the forward direction, their collision frequency is reduced as they collide less frequently with one another. Finally, at time 2, we're going to have this as our relative equilibrium here. So the collision frequencies between A and B stabilizes, meaning the frequency stops changing. So this means to say that A's and B's are being turned into C's and D's at the same rate that D's and C's are reforming A's and B's. So for every A and B consumed, another A and B is produced by the reverse reaction. So the collision frequency in C and D stabilizes, meaning this rate stops changing. So the relative rates of the forward and reverse reactions, the reactions occur at equal rates. So for every A and B collision that forms C's and D's, a CD will collide, forming or reforming those A's and B's. Now, a couple of the discussion questions I want you guys to look at here. There you go. It says, during time 1, how did the buildup of products interfere with the collisions of A and B? Describe the process of negative feedback inhibition and how it impacts the forward rates. How about this? It's hard for an A to find its bay with all those C's and D's in the way. Enjoy that one. Number 2, describe the dynamic equilibrium in terms of the example on the front page. So I want you to use terms like AB collision frequency, CD collision frequency. Let's use the collision frequency and that kinetic collision model to explain dynamic equilibrium. Let's use those terms in this answer. And final question, what would happen if we increase the temperature on this system? Well, temperature is a measure of kinetic energy at the molecular level. So the rate at which A's and B's are pinging off each other and the rate at which C's and D's, they're both affected by temperature. If more energy is available, one of those two reactions might happen more often. The one that has higher energy requirements will occur more often if more energy is available. So that could cause, when the rates are equal, to vary or change. So I'll get you to think about those 3 things. Make an effort, answer those questions. We'll discuss. Thank you very much. Bye, everybody.